In this fourth and last video for the control lab, I'm going to help you a little bit with Matlab commands. For that, I have prepared here an M file, identification interpretation. If you open it, you will see that you have commands to clear the workspace and close all figures, and then we load this mat file that we have generated after the first experiment. If you run this, you generate this figure again because it was saved, and you can see that in the workspace, well, you have the variables after the first experiment. You can see here the time vector t, the input u, and the output y of the original data, and here tm, um, ym, this is the data after cleaning. So what we can do now is use this data to produce a plot of the first experiment. What I've done here is add some code that allows you to plot the experimental data. Using the subplot command, you can plot two plots one above the other. The first plot is the input data, hence the label MV, and this is here the output data, hence the label PV here, and the X label is of course time in seconds. You can give this a title, and if you run, this is what you obtain, right? And well, the problem we have here is that the first data point is at 23. So what we can do here is remove this first data point, because obviously this is an incorrect data point, and you can do this as follows. So you redefine t, u, and y by only taking the second point up to the end, so you reject the first point, and this is what you obtain, right? This is the step response that we have performed on the system. The heating power has been changed from 30% to 70%, and this is the response, the original response that we had obtained. And of course, you can do something very similar for the cleaned data, and this is what you obtain. Here you have this unit step at the input and the corresponding response of the system. So here everything is brought back to a 1% change in the heating power, and we can see the corresponding response, and we had seen that the static gain is indeed around 0.6. So what I would like to do now is compare our experimental data with what is simulated using our Van der Grinten model with these parameters. A Van der Grinten model is a gain, two time constants, and a delay. So what we need to do here is, use the parameters that we have identified, and here they are, and what we'll do is compare the output of the model with these data that have been cleaned here, because these are the data when working around the working point around MV at 50% and DV at 50%. So these are the parameters that we have identified for our Van der Grinten model structure, and now we can construct the transfer function itself. So first of all, we have to define the S variable. This is how this is done, and this constructs here our Van der Grinten model. Again, two time constants, t1, t2, and a delay. And what we can do now is obtain the step response of our Van der Grinten model, right? For that we use the command step, and we use the same time axis as over here. Remember that this is the cleaned data. So this is going to provide us the step response of the identified model, and what we can then do is plot the experimental data and the step response of our identified optimal van der Grinten method. You can add a label for X and Y as before, and it's nice to add a legend, and this is what is produced. So here it is. In blue, the experimental data, and in red here, the step response, the unit step response of our optimal identified van der Grinten model. So what I've done here is added the code to produce a Bode diagram. If you run this code, this is what you obtain for the Bode diagram. Here you have the magnitude Bode diagram, and here the phase shift Bode diagram in terms of the frequencies. You should discuss this in the report. This is something that we have tackled in the theoretical course. In the assignment, you will see that during the first control laboratory, you will have to obtain 3 other models using graphical methods. So the first model is a Bruyne model, first order with delay. You'll have to obtain another van der Grinten model, obtained using graphical methods this time, and a stretch model. So this is again a delay and n time constants, right? The method is explained in the assignment. So the easiest thing to do is to work on the experimental step response, measure the things that you have to measure, for instance T1, T2, then compute the parameters, right? Do this directly in Matlab and produce the transfer functions. The transfer function for the Bruyne model, the transfer function for the van der Grinten model obtained using graphical methods, and the transfer function for the stretch model. And then of course what you should do is compare all those step responses with the experimental data, compare all the Bode diagrams, and discuss what are the differences that you see, why are those differences there, and so on. So this is how the comparison should look like. This is of course on another system. You can see it here because the static gain is above 1, right? And in the example that we had discussed, we had around 0.6, but nevertheless this is how your comparison should look like. You should have the actual response, so the experimental response here given in dark blue, then the step response of the 3 models obtained using graphical methods, 1 Bruyne model, 1 van der Grinten model, and a stretch model, and then finally you should have the van der Grinten model obtained using optimal identification. And of course then you should discuss the differences. You can have a look here at what happens at the start, and well, have a look at the differences that you see with respect to the experimental data. And in terms of comparison of the different Bode diagrams, this is how it should look like. Again, this is for a different system, but you can see that we have the Bode diagrams of the 3 models obtained using graphical methods, the Bruyne model, the van der Grinten model, and the stretch model, and this is compared then with the van der Grinten model obtained using optimal identification, right? And again, you should compare these models in terms of the high frequency slope and the phase shift.